chill YouTube channel. This is a channel I made with a couple friends. It's a co-creator over there. Another one over there. Flip the camera around. Alright, so the first thing we're talking about on this YouTube channel is cellular respiration. So the first step in cellular respiration is glycolysis. So the thing about this guy, he takes this glucose molecule, which is this guy here, and basically breaks it into 2-pyruvate. This guy is actually kind of funny, right? It happens at a substrate level, it occurs in a cytosol, and no carbon is released. So if you look at the reactants here, we have glucose, ATP, and electron carriers. And after 10 enzymatic reactions, we get 2-pyruvate, again ATP, NADH, and 2H+. Now we have this nice diagram here that also shows the glucose being broken down into 2-pyruvate. And so this is the first step in cellular respiration and making ATP.
Oxidation occurs when a molecule loses an electron. In this step, it would start in the cytosol and move into the mitochondria. Pyruvate is used as an input in this cycle, or in this process, which then has an output of CO2. NAD plus is turned into NADH, which is then used in acetyl-CoA, which goes into the Krebs cycle in the mitochondria. Right here.
So today we're going to be learning about the Krebs cycle. So we start off with the acetyl-CoA, and we move on to the CoA being taken out, which leaves us with citrate. Now, this cycle is accounting for 2-pyruvate. So we have 6 carbon, which means we have 3 carbon for each pyruvate. So, moving from the citrate, we get 2 NAD pluses that turn into NADH plus CO2 when they become electron-carrying molecules. This next phase has us taking the ADP and the inorganic phosphorus and turning it into the ATP, which is our energy source. Then, from there, we take the FAD and turn it into FADH2, which then, in turn, makes it an electron-carrying molecule. And then again, we take another NAD plus and turn it into NADH, which has electron-carrying molecule properties. And then from there, the Krebs cycle finishes with 4 carbon with what is known as oxaloacetate. So, as we can see here, we have the change in Gibbs free energy on the y-axis and the reaction proceeding as the time moves on the x-axis. From the graph, we can see a lower affinity on the left and the higher affinity on the right for electrons. So, starting from the very beginning, we take the 1, which has 1 electron, and we move it to the 3, down the transport chain, and the 2 also moves its 2 electrons to the 3. From there, we take the 4 electrons and transport to the 4, and then take those and get to the byproduct of O2, which has the highest electron affinity and makes sure that all the electrons are accounted for. Now, we can see this in the matrix of the mitochondria, where from the leftmost hand side, we go through the electron transport chain, and you can see all of the steps taking place to where ATP is synthesized. And as a result of the O2, we have the H2O as well. This happens at the end of the electron transport chain, and to get from 1 to 2, we have to use the Q coenzyme, and to get from 3 to 4, we have to use the cytochrome C. So